Welcome back to A-Star Science, part of our GCSE Must Know Chemistry series. Today we're going to talk about fractional distillation, and this relates to all the other topics in organic chemistry. So when we look at organic chemistry, we are looking at carbon-based molecules, specifically hydrocarbons. So these are molecules that contain carbon and hydrogen. We remember that these types of substances are covalent in nature, meaning they have a nonmetal bonded to another nonmetal. In this case, you'll see the first nonmetal is the carbon and the other nonmetal is hydrogen. And so this makes them what we call simple molecular structures or simple molecules. So they are molecules, and I'm going to draw a little circle around here. So when you have these molecules, you don't just have one molecule. In any volume of space, you have many of these molecules. Now, while the bonding inside the molecule or between the carbon and hydrogen is a covalent bond, and that is quite strong. Between the molecules themselves, there are very weak forces. So we call this weak intermolecular, inter meaning between, intermolecular, molecular meaning molecule, forces, which we say IMF for short. So between the molecules, there are weak intermolecular forces. And so this is where fractional distillation, which is a physical process, can be used to separate these hydrocarbons from each other. Another key concept is remembering that many of the hydrocarbons are obtained from crude oil. Crude oil, which is that black mixture, black liquid that comes from the ground, is a mixture of hydrocarbons. And this is important to understand because the fact that it's a mixture means that we can use physical processes to separate the different components. Okay, and in this case, the physical process is something we call fractional distillation. Now, what does that actually mean? So when it comes to distillation, an easy thing to remember is distillation refers to first, it refers to boiling, okay, or heating, which then causes evaporation, which then causes afterwards, doesn't cause, sorry, but then we condense or condensation. So fractional distillation is using this process of boiling, aka heating, causing it to evaporate, and then condensing the substances back in order to separate them. Now, the reason they separate is that they have different boiling points. And we're going to look at this in a minute. They have different boiling points. And so because they have different boiling points, when you heat them up, they will evaporate at different temperatures and then condense at different temperatures. And so we can use the process of fractional. Fraction means to separate into parts, like a fraction. We can use the process of fractional distillation in order to do that. So just remind yourself again that distillation refers to the process of, let's correct that. Distillation refers to the process of boiling, aka heating, then evaporating, then condensing. Okay, so let's look more specifically at how fractional distillation is carried out. So on the picture, you'll see that we have a distillation column, and these distillation columns used in industry to separate and do fractional distillation for crude oil are very, very large. And so what first happens is the crude oil is sent into the fractional distillation column. And when it gets into the fractional distillation column, it's heated. And as we said, the different components have different boiling points, and they start to evaporate and rise up the column. So they evaporate and rise up the column. Those with the highest boiling points, they will stay at the bottom of the column because they take a lot more temperature in order to, a lot more heat in order to evaporate. So they tend to stay at the bottom of the column. But there's those with low boiling point, they will make it to the top of the fractional distillation column. And when they get to the top, these different gases will either condense, or some of them just come out as gases themselves at different levels on the fractionating columns. Now, what makes them separate? A key factor that we have to remember, because they are covalent molecules, we said, even though they're quite long chain, some of them, is that the longer the chain of hydrocarbon, the more IMF, or intermolecular forces, which means that they require more energy to overcome these forces. So because the short chains do not have much IMF, they don't require much energy. That's why they'll be at the cool part of the column. Whereas the long chains are at the bottom of the column. Some of them do not even evaporate. Some of them stay as a rather viscous solid, such as the bitumen, which we're going to talk about in a minute when we look at the different products. So the short chain hydrocarbons, they do not have much intermolecular forces, so they don't require much energy to overcome. So it doesn't take much heat for them to evaporate, and they go to the top of the column and then can be extracted there. That's the cool, relatively cool area of the column. Whereas the long chain, the very long chain hydrocarbon molecules, they will stay at the bottom because they have a much higher boiling point, and this is the hot area of the column compared to the cooler area at the top. So now that we understand the process of how fractional distillation is carried out, let's look briefly at some of the products that can result from the fractional distillation process, remembering that the bottom of the column is the hot area, and so we're going to get the long chain hydrocarbons collecting there, and the top of the column is the cooler side, although it's still hot, but it's relatively cool, and we get the shorter chain products there. So right at the bottom of the column, we have a very long chain products, such as bitumen, which is a type of tar used to waterproof roofs as well as to put on asphalt for our roads. So it has very long chains, and so it takes a lot of energy to overcome. So it's very viscous, meaning it's very thick. At the top of the column, that cool side will get lots of the gases coming out. Butane, things like LPG, which is liquefied petroleum gas, natural gas, things along those lines will come out at the top. They are very short chain, so they quickly rise to the top. They don't take much heat, and then they will condense. And some of them don't even condense. They come out as gases because the boiling point is very low. Even the petrol that we use in our cars can come from this crude oil, and that can be siphoned off once it condenses. And you'll find that towards the top of the column, it has a shorter chain than others, and that's why it's so flammable. And underneath that, you can get kerosene. Kerosene can be used as airplane fuel, contains a lot of energy, and but it is a longer chain than petrol. And finally, in between that, even the diesel fuel that our cars run on comes from this process as well. And we know that diesel is much thicker than petrol, and that's why you'll see it underneath petrol on the fractional distillation column. So remembering that as you go up, you have the long chain hydrocarbons at the bottom and the short chain hydrocarbons at the top. And all of that is to do with the decreasing as you go up the column, intermolecular forces, which you'll write as IMF. And that means that they require less energy to overcome, less energy to turn into a gas, and they tend to come out at the top of the column.